William, can you hear and see my notebook right now?
Yes, sir.
Okay, thank you. So we'll begin here. Just gonna wait a moment to see if the other ladies get back in with us. And Megan is back. You can hear and see the notebook, Megan?
Yes.
Okay. Does my voice sound normal? Whatever that means.
It's a little crackly, but
Yeah. Yeah, I don't know why that happened yesterday as well, and for part of the day, and the other part it didn't. I'm not sure. Too many things can go wrong, appears. Well, nonetheless, but you guys can understand me, yes?
yes.
So, okay. You can unmute yourself, blah, blah, blah. Okay. All right, so hopefully Griselda comes back. And so the first thing I want to do is share with you some of our basic functions we've been looking at throughout the semester, and also pinpoint a few details that I want us to be specifically aware of in order to help us do what we're going to do today. So you can either take a picture of these 5 graphs, but I think only they kind of just fit here, I think. So here's 1, 2, I went all over the place here. 1, 2, 3, 4, and 5. There are the 5 basic functions I want us to keep in mind, and showing you some specific details. So you guys, if you wish to take a picture of them, do that now, because I may go a little too fast for you to draw them all right at this moment. So, and then I'm going to refer to them as we do the work. Okay?
Okay.
Did you guys get a chance to take a picture if you wish?
Yes.
Okay, William? Okay, so looking at the first graph, well, I just called it number 1, no particular order. And we have here the basic equation of a line, or we call it like the originating line or linear function, and it's y equals x. Sometimes they call that the parent function for a line. And here's Griselda. So, and the thing I want to point out to you that I will need to look at is the following. So of course, this line y equals x passes through the origin, and the slope is 1, but so that really means if you go over 1 unit, then you go up 1 unit, and you have to be right on the line, okay? So over 1, up 1 is on the line. And the same thing if we go backwards, we move left 1 and down 1, and we're back on the line. So the reason we need to talk about these things is because in a moment, we're going to learn how sometimes a new graph, a new function, there's like a multiplication of a number done to the function that will do one of 2 things. It will, well, indirectly, it can do both kind of at the same time, but I don't want to make it sound confusing here, but we'll specifically be looking at 2 possibilities. One of them will be all these points on the line, there's an infinitely many of them, of course, but I just want us to concentrate on these three basic ones here. I mean, these three I have outlined, and that is the transformation, the dilation, which is a stretching effect or a shrinking effect, and it can be looked at in two perspectives. One is away from, closer to, away from the y-axis. So closer to the y-axis would be the point moves in like 1/2 as much. Whatever that distance right there is, it may be the new equation is telling us, even that's what we're going to learn today, is how do we recognize when it's telling us that it is now, the new graph won't be this one anymore, but it comes from this originating linear, basic linear function, or we say the parent function of a line. And it'll tell us, oh, move all these points either closer to the y-axis or away from the y-axis. Excuse me.
Bless you.
Bless you.
Thank you. Griselda, I'm sharing your pain, okay? Allergies. But anyway, so now if that occurs, then if it's close, so closer to the y-axis, away from the y-axis, this is a horizontal movement. These points are going to move. This point, either if it's all these points are going to be closer to the y-axis, we call that a horizontal. Same if it's away, because it's a horizontal movement. And it's either a horizontal stretch away, meaning further away from the y-axis, or a horizontal compression or a shrink, which means the distance from the point on the line to the y-axis becomes a fraction of what it was before. Maybe 1/2 the distance, or maybe 1/3 of the distance, or so forth, or maybe 3/4 of the distance. If it is away from if all these points move away from the y-axis, well, then that's a horizontal still. It's a horizontal dilation effect, which in this case we say more specifically a stretch. So this distance right here is 1 unit away, because remember the points that I want us to keep in mind for these 5 graphs are the following. For the basic line, because the slope is 1, if you go over 1 unit, you go up 1 unit, you're back on the line, like I already said. And the same with if you move 1 to the left and then you move 1 down. So, and right here, that's on the origin. By the way, if we're asked to stretch this distance away from the y-axis, that's a horizontal dilation, and more specifically, a horizontal stretch. If they say it's a stretch with a scale factor or a multiplied factor of 3, just pretend, then you're going to say, oh, this special point that I want us to keep in mind, I could pick other points, but I just tried to pick ones that we'd be more likely to be familiar with from the basic graph, the y equals x, and y equals x squared, and the square root of x, and the absolute value of x, and so forth. If they say, take all these points on the line and do a horizontal dilation, but more specifically a horizontal stretch by a factor of 3, so then this point, which is currently 1 unit away from the y-axis, that distance, now the new equation, the new graph, if it's stretched horizontally by a scale factor of 3 or a multiplied factor of 3, then it's going to be not just 1 unit away, but 3 times that. So 3 times 1 unit would be 3 units. So it'd be stretched over to 2, and it would stretch out to another unit, 3, and this point on the original graph now would be way over here, like that. And so this whole distance now is, this point now is 3 times the distance that it was originally from to the y-axis. And we would do that with all the points. So like this point, if this was 2 up and 2 over, then this distance now, which is 2 units, would now be triple that, which would be 6 units, and it would be way over here or something. This point, but we don't need to do it. We only need to do it for these 2 key points, and then the rest we just connect the line. So that's why I just want us to concentrate on these 3 points for the line. And likewise, this point over here, if they tell us to horizontally stretch it by a factor of 3, that means currently this is 1 unit from the y-axis, and now when you perform the dilation effect, the horizontal dilation effect by a multiplied factor of 3 or a scale factor of 3, well, now this distance won't be the 1 unit, but 3 times that, which will move it over to -3. And now this point will move over to this one. And now, by the way, if you're right here on the origin, are we away from the y-axis if we're on the origin, or are we on the y-axis?
On the way.
Oh no, why?
So there's no distance. This point has no separation from the y-axis, does it? It's not a little bit to the right or a little bit to the left. It's right on the y-axis. It's also on the x-axis as well. But just think about the y-axis, okay? So if we tell, that's like saying, okay, you have no money, you have 0, Mr. King has $0 to his name. Now multiply that, because we want to make you feel better, Mr. King. So we at the bank, your friendly banker is going to give you 3 times that amount of money just to make you feel, because then we know times are tough. So, and now they say, okay, oh, I'm so sorry, Mr. King, but 3 times $0 is how much?
3.
Zero.
Is it
Oh,
$0, right? I wish it was 3, Griselda, yeah. But it's still 0, isn't it?
yes.
So what I'm trying to say is, if your point is right on the, if it's this point on the line is right on the y-axis, and now they say stretch this, the distance this point currently is from the y-axis, stretch it by a scale factor of 3. Well, if you try to multiply the distance, you are away from the y-axis, but you're not away from the y-axis. So if you stretch it, it's still not going to move. Does that make sense?
Yes.
Yes.
Only if you shift it and you say, oh, move it or slide it or translate it 3 units to the right or 3 units to the left or like that, then you actually move it, but not when it's a multiplying factor. So only the points that are not, see, all these points that are on this line here that are not on the y-axis, well, when you say stretch it horizontally away from the y-axis, well, now that will stretch. But if you're right on top of, if the point's right on top of the y-axis and you say stretch it or shrink it, it's not going to move at all. Does that make sense?
Yes.
So then this new line, so this point would not change at all after you perform that horizontal dilation effect, that multiplied factor of 3, it wouldn't move. So now you would have this new point, and this point didn't move. And now when we connect it, here's the new line now. Okay, so this equation now is an alteration of the originating linear function y equals x. And what it is y equals, it comes from the originating function, linear function y equals x, but it has been stretched horizontally by a scale factor of 3. So what you do in that case is And this one's a little strange because all it is y equals x. Versus these other ones, it'll seem different. But for the moment, it may sound, you may not completely understand it, but what you do is you take the equation that it came from, the y equals x, and now you do a multiplication of a scale factor of, and for right now, I'm just going to ask you to believe it, but whenever we, and you might remember, whenever we have done this in class, which is slide it or slide a point, the graph to the right or to the left, you always do the inverse of that. So if you have like, for example, if you have absolute value of x plus 4 inside, well then because it's a change next to the x, that's a horizontal change, and you do the opposite of it. So when we said plus 4, we didn't really move this whole graph 4 to the right. We moved it what? 4 to the what?
Left.
To the left, yeah. So then you always end up doing, when you move with respect to the x dimension, the equation that is written, it has the multiplicative, the mathematical inverse operation on it. So here we wouldn't say times 3, because when we move with respect to the x dimension, you have to, whatever is written in the equation is the mathematical inverse operation to what we actually do. So we actually stretched it or multiplied the distance by 3 horizontally with respect to the x dimension. So the equation is going to look, it's not going to say times 3, because it has to be the mathematical inverse operation of multiplied by 3. And what is the inverse operation of multiplication of 3? It's what?
Division.
Divide.
Division of 3. So we could put an x over 3, or we could just write in front of it a 3, I'm running out of space there, that looks pretty bad, 1/3. So, sorry. So this would become y equals, and instead of x, the effect is going to be the mathematical inverse of multiplication of 3, which is division of 3. So we could write it like that. And this is a dot, that's nothing there. Or we can write it as inside with the x, instead of saying division of 3, we can just write 1/3 as well. So either way, okay, this and this are the same thing. So, because it's like x over 1, so denominator times denominator is 3 times 1, which is 3. Numerator times numerator is 1 times x, which is x. So I hope you agree this is the same as this, yeah? Okay, so you might still kind of be lost, but hang in there if you are. So now I want to show you some basic ideas. It'll end up being very, very nice. Just hang in there. So here's a second basic graph that we need to be aware of, and it's y equals x squared, and that's the parabola. Sorry for the delay. It's the basic parabola graph, x squared. And this is what it looks like. It opens up. We've talked about this graph before, but I want to point out something in particular that we're going to need, because we're going to start thinking about stretching the points either closer to the y-axis or away from the y-axis. And that's that horizontal dilation effect that can be performed on an equation, okay? And also, today we're going to look at it vertically as well. a point can be also thought of as compress it or shrink it, the point vertically this way, closer to the x-axis, or stretch it away from the x-axis. But for right now, we're just going to concentrate on this one, okay? Looking at it horizontally, all right? So what are the key points that we need to, that I would like us to take special note of and remember is this. Just like this one was 0, 0, and then over 1, up 1, left 1, down 1. On this one, I would like us to remember, well, 0, this point is 0, 0, because 0 squared is 0. And the next one is 1 squared, 1 times 1 is 1. So if you go over 1, then the mapping goes up to 1. And the same to the left, left 1, up 1. And then also over 2, 2 times 2 is 4, if you put 2 in there. So 2 squared is 4, so the mapping's up to 4. And same thing to the left. If you go left 2, negative 2 squared, negative 2 times negative 2 is 4, so you also go up 4 there. So what could happen is, in a few moments, they could tell us, oh, this basic parabola is changed, and now they could tell us, hey, perform a horizontal dilation, and by a multiple, so say it's, I don't know, say we say 1/2 by a scale factor of 1/2. So then that means the distance to the y-axis. So right now this is, this point right here is how many, this key point right here is how far away, how far is this point right here to the y-axis? Don't say 4 units, that's 4 units up. How far is it horizontally?
2.
2, good. And if we say compress it or shrink it by 1/2, well then half of this distance would be, instead of 2 units being, this point being 2 units away, now you're gonna go half as much. So now it would only be how far away?
1.
1. Okay, so this point moves in by 1/2 the distance that it currently was. And the same with this one. Just think of these key points. And how far is this point right here away horizontally to the y-axis? Currently, right now, it's how far is this?
1.
1. And what would be 1/2 of that?
0.5.
0.5. So it would move half the distance closer. And this side, the same thing. And this side, the same thing. And what about this point right here that's on the y-axis? Does that have any distance away from the y-axis if it's right on top of the y-axis?
No.
So if we say compress it closer to the y-axis by 1/2, well, it's not going to move, is it? Because it's already on the y-axis. Does that make sense?
Yes.
Okay, so then this point will stay. And then the new horizontally compressed parabola will look like this as a sketch instead. Does that make sense?
Yes.
Yes.
And the equation would be, you would take the basic, and I'm putting it in a parenthesis to emphasize that the basic function is x squared, and the x is inside of the powering function, the powering of 2, or we say the squaring. And so when we say perform a horizontal dilation by a scale factor of whatever, then when we rewrite it, then we're still going to have x squared and what's going to occur next to the variable x? Well, it's gonna, if we compressed it by 1/2, so the scale factor 1/2 of 1/2, then right here, we're not gonna say times 1/2. We do the mathematical inverse of times 1/2. And what's that? What's the mathematical inverse of times 1/2? Or you could say dividing by 2. Because dividing by 2 is the same thing as saying 1/2. So what's the mathematical inverse of dividing by 2? It's what?
Multiplication.
Multiplication of 2. And so this would be our equation of that new, whatever this color is, graph. Does that make sense?
Mm-hmm.
William?
Yes, sir.
Griselda?
I'm sorry. I wasn't paying attention because I was doing my notes.
Okay.
I'll just
Oh,
rewrite it.
Okay.
And I'll look at the video.
Okay. So we're gonna practice plenty. So if you could always take a picture, or like you said, go back and look at the video. Okay. So now I'm not gonna show you examples so much because we're gonna do plenty of that when we do the homework. So now I'm just gonna show you the 3 remaining basic graphs that we're gonna be asked to perform these dilations. And that is, I just said this one's number 3, no particular order. Y equals x cubed. And I want us, if we were to plot points and make a little table, I'm just using these key points, -1, 0, and 1. And notice I've been doing that with all of them so far. And if you do cube them, you would get -1, 0 times 0 times 0, 0, 1 times 1 times 1 is 1. And here are these key points. 0, 0, 1, 1, -1, -1. So we're going to remember that on the cubing function, when you go over 1, then you better move, if you move up 1, there's a point, there needs to be a point right on the graph there. And the same thing, if you move left 1, then down 1 is a point on the graph, because those are points on the graph. And 0, 0 again is right on the y-axis. So if we compress or stretch this point away from the y-axis, it's not going to move again. Any questions there?
No.
And a fourth and a fifth graph. The fourth one is the absolute value of x as the originating absolute value function. And no translations have been performed on this, nor any reflections, nor any dilations. And here are the key points. Again, we could make a table again, but I just, instead of making the table, I'm just showing you here. If you put 1 in, you get 1. So again, it's this 1 over, 1 up. The left 1, up 1. And put a 2 in, the absolute value of 2 is 2, so 2 maps up to 2. The absolute value of -2 is 2, so -2 maps up to 2. So again, we have this over 1, up 1. Over 2, up 2. Oh, I forgot to mention here, we could also use another additional 2 points here. 2 over, and 2 cubed is 2 times 2, which is 4, times another 2, which is 8. So 2 over goes up 8, 2 to the left goes down 8 to -8, like that. Okay. And the fifth and last one is the square root originating, the original square root function, or we say basic function, or the last 20 years or so, they started saying parent function. Before that, we never heard of that before. But anyway, the parent function then. And that is, the domain starts right here at 0. There's no graph to the left, because you can't take the square root of a negative number. And I mean, it doesn't give you a real number, so there's no mappings, there's nothing. Okay, so 0, 0, because the square root of 0 is 0. So all 5 of these graphs have the point 0, 0 on them, yeah? And the square root of 1 is 1. So here's another 1 over up 1. Matter of fact, every single one of these 5 graphs has that. This is one, though, that doesn't have any, this is the only one that doesn't have anything to the left, unless we move it, yeah? Or reflect it, or, yeah. So, and then the other nice one I want us to remember is the square root of 4, because that's just a nice simple integer answer. The square root of 4 is 2. So over 4 up 2. And now we're going to be asked in a moment, take this graph, all the points, but we only need to look at a couple key points. And that's what I'm calling these, is the key points I want us to emphasize in our minds when we are asked to do these changes, these transformations, and specifically dilations. We'll be asked to take these key points and either compress it or shrink it the distance closer and closer to the y-axis by a scale factor of whatever, or stretch it away from the y-axis, which would be a horizontal stretch, okay? And we are going to also do it vertically away from the x-axis, and but we're going to first concentrate on the horizontal one. Okay, so let's go to homework problems and take a look. So, and 1.7. Okay, so don't be unnecessarily intimidated. There's a lot of questions here, but they're mostly, once we learn it, they're mostly quick questions. Okay, so don't panic. Okay, I'm going to jump right to what we were talking about, which is towards the bottom of the assignment. See, notice these problems, for example, this one, the multiplication of the basic function or parent function square root. Where is the multiplication occurring here, guys? Is it inside the function next to the x variable or outside of the entire function?
Outside.
Outside. Instead, it could have been times 2 inside. Inside the function next to the variable x. When it's multiplied outside, that's when it's going to take the points of the basic square root function, and whatever the distance is to the x-axis, it's going to stretch it away from the x-axis or shrink or compress it closer to the x-axis. That's when we multiply the entire original parent function by a number, but on the outside of the function, not inside. Inside is the one I was just talking to you about, yeah? When it's inside the function and there's a multiplied number next to the variable x inside the parent function. So that's not this. So this is going to be the vertical dilation, and so is this one, because the times 1/2 is outside the this number is multiplied by the whole function square root of x, and it's outside, not inside, next to the x variable. Oh, so here's one that is inside. So it comes from the absolute value graph, which, remember, is from my, I don't know if you guys have your picture or note, but I can show you again from my notebook, I guess. So remember our absolute value parent function is this, and the key points are the 0, 0, over 1, up 1, left 1, up 1, over 2, up 2, like that. And now we're going to be asked, there's a multiply 2 right there inside the absolute value function next to the x. And so that means that's supposed to be telling us, so these are really the two things that are very new to us, at least in our class, is to understand what is that multiply 2, what kind of impact does it have on this original parent absolute value function. And anytime the variable x is multiplied by a number and it's in that multiplication of the number is inside the function, not multiplied outside the function, inside, then that's when we are going to do the mathematical inverse of whatever it says inside, and we're going to then either stretch it further away from the y-axis or shrink it or compress it closer to the y-axis. And what was there in our problem class? What was inside here? A multiplication of what?
2.
2. So instead of thinking to yourself, multiplied a factor of 2, yeah, which would be a stretch, but we have to do the inverse, the mathematical inverse operation of multiplication of 2. When we actually change these key points, we're going to do what then? Not multiply this distance to the y-axis by 2, but do what to it?
Divide
Divided by what?
2.
2. Are you guys okay with that?
Yes.
William, are you okay with that? William, are you still there? I think some people, you guys just go out in the backyard and have a lemonade and go jog around. I'm just kidding. I don't know. Okay, so yeah. So this point's gonna move what then, class? Is it gonna move away from the y-axis, a stretch, horizontal stretch, or a horizontal shrink or compression?
Compression.
Compression, yeah. And it's gonna be whatever this distance is right now, and same with this point and all points, it's going to be compressed. It's going to be half the distance, division of 2, yeah, which is the same thing as half. So then,
Compression and shrink are the same thing, sir?
no, shrink is when it gets closer.
Uh-huh.
Stretch is when it gets further away.
Okay.
Does that make sense?
Mm-hmm.
So I know it says multiplication of 2, but what are we supposed to think when it's a horizontal effect? Do we do what it's the mathematical operation tells us, times 2, or the inverse operation?
No, we divide it.
Yeah.
Over.
Does that make sense? So then this distance was, how far away is it? See, now I can draw on this. So how far is this distance currently, Griselda? Pretend I can,
2.
2 units, and now it's going to be what? Yeah? Is it going to be, this is 2 units away from the y-axis. Is it going to be now twice that and say 4? Or is it going to be half the distance?
Half the distance. So
And what is half of 2 units?
1.
Good. So now you're going to be only 1 unit away. 1 unit away from the y-axis. So this point moves in, it moves in by 1/2 the distance, or division of 2. Is that okay? So it's going to be a point, this point on the original basic absolute value now is right here instead.
Okay.
And what about this one, Griselda? How far is it currently away from the y-axis?
1.
1. And so 1 unit now is going to change because now we're going to do what? Not leave it as it is, but what?
Divided, which is half.
So now this point, you're going to say, oh, it's only going to be a half a unit from the y-axis. So you go from here and you go 1/2 a unit, and you would be like right here somewhere.
Yes.
Is that okay?
Yes.
And see, all of these points are going to do that. They're all, I'm just asking us to concentrate on these 3, or these on this side as well. I mean, all of them are going to be closer. They're all going to move in. It's going to be half the distance. So, but if we don't have to do like, 100 points or something. We just have to pick a few. And and this one will be the same thing, half the distance. And this will be half the distance, which is 1 unit away. And, however you want to draw this, and I hope I'm not making, what about this point right here, Griselda? How far is it right now away from the y-axis?
It's 0.
So what happens if you now move half the distance closer?
It's gonna stay in place.
It's going to stay in place. Very good. And now you would connect these new points, and now this becomes this is the graph, and this is just a sketch, so sorry if it doesn't look that great. I mean, I don't have graph paper here. Oh, I'm going to destroy it. So, but anyway, I hope we can understand that my scalings are not perfect here. And this would be the new graph, which is, what did we just do? What were we told to do? Take the, it said times 2, but then we're supposed to know, that's what we're learning right now, is then what that really means is the mathematical inverse of multiplication of 2, which is division of 2. And what about division of 2? It's the original points, that distance from the y-axis. So it's 1/2 the distance, okay? So this is a horizontal dilation, but more specifically, a horizontal shrink. And by a scale factor of 1/2, yeah? Any questions there?
No, sir.
No.
You got a new computer?
No, because?
Oh, because you're drawing on your notebook.
Well, it looks like I'm drawing on my notebook, but I'm just drawing on my monitor.
Oh.
And then it's magic, huh?
Mm-hmm. That's cool.
So, pretty cool. Now over here, though, I was drawing with a pencil. So that's on my notebook, but not this part. Okay. Okay, so we go back to our WebAssign. And, okay, Megan, what does it ask us here? Can you read this part?
The function g is related to one of the parent functions described in an earlier section.
And then and then letter A?
Identify the parent function f.
And what was the original parent? What is this coming from the course? Which one of those 5 that we've been looking at?
The absolute value?
Mm-hmm. So then we can type ABS and that'll show up, or we come over to our little, whatever this is called, the calc pad, I guess, calc pad. And we look for the absolute value function, which is that one. And now we just put the X. Oops, we're not capital. And then, now letter B, Megan.
describe the sequence of transformations from F to G. Select all that apply.
So what did this one do right here again then, guys? Soon as you see multiplication of a number, that means dilation, which means either a shrink or a compression. A shrink or a stretch. And it's either horizontally stretching away from the y-axis or shrinking closer or compressing closer to the y-axis, or it is the points shrinking or compressing, which means the same thing, shrinking or compressing closer to the x-axis or stretching away from the x-axis. That's a vertical dilation or a vertical stretch or a vertical shrink towards the x-axis. When you go vertically, now you're talking about the other way, and you're either getting closer, vertically shrink, or vertically stretch. And when is that going to happen again? When the multiplied number is not inside the basic function, but outside the basic function, okay? And so which one? It's not a reflection, it's not a shift, so it's one of these two.
Horizontal shrink.
So it's a horizontal shrink, and I don't know why they didn't say exactly what it is. But anyway, we would say by a scale factor of 1/2, yeah?
Uh-huh.
Is that okay?
Yes.
So we just click this one, and now we match. So now you got to remember our original picture. So doesn't the original absolute value graph, it comes down right here, and they come down here and they touch the origin, the two line segments, or lines, rays. So, and what have we been saying a few times already? What does the original one do? What were the key points? 0, 0, and then what? 1 over and
1.
1 up.
1 up, yeah? So that's the original, okay? And now what are we doing to this? So I guess I could draw it here. Doesn't matter which one I draw it on, I'm just drawing it. So the original one is 1, 1, 2, 2, origin, 1, 1, and 2, 2. And it looked like, if I can keep this straight, this is very challenging, okay, ladies? Okay, guys? And I just blew it. As soon as I said it was challenging, oh, I better erase that. Sorry. And let me try again. And oh, I jinxed myself now. And I'm not capable of doing anything at the moment. Okay. That was the original. And now we're going to compress it closer horizontally to the y-axis. Now the question is, which graph does it have to be? Well,
Sketch A.
yeah, it's A. Because this one is what? By the way, if this one, you can tell it's not compressed, because if you move over one from the vertex and you go up one, you're still on the graph. So it didn't change. It didn't I don't know how to say it. This V part didn't become closer together or stretched out, open up or closed more. And this one just is shifted over 2 units to the left. Yeah? So this would be a translation, a horizontal translation. And remember what this one would be. So now we can have a little review of what we've learned already. So what happens when you shift it, or that's called a translation or a shift horizontally. You do it, you write it inside because it's with respect to the x-axis, And how many units does this one look like? One, how much of a shift?
2.
2 units. But you have to write in here the mathematical inverse of what visually occurred. Because when it's horizontal, you have to write in the equation the mathematical inverse of what it does. Or if you think of it, well, anyway, so instead of saying subtract 2, you're going to have to write what inside here? What's the mathematical inverse of subtraction of 2?
Plus 2.
Plus 2. So that's what this one is. This one, if you look here, if you go over 1 unit and you go up 1 unit, it looks like you go right back on the graph. Over 1, up 1. Over 1, up 1. So this V shape here, it's not like you squeezed it together and it's now not as open. This part, I mean opening, like this angle doesn't change. And it doesn't open or become closer, and it doesn't open up and be a bigger angle like something like this. But the key is if you just look 1 unit over and 1 unit up, well then you're right back on the graph. So this is cannot be any kind of dilation, either closer to the y-axis, further away, or even to the x-axis, even closer to the x-axis or further from the x-axis. Because if it was, then it would not be 1 unit over and 1 unit up and being right back on the graph. So what is this one? Yeah, it's what? It's not a dilation effect. It's not a reflection. It's a translation, but not to the left like this one was, but what?
Vertically.
Vertically. And if we were asked to write this equation, so I'm kind of using this problem to teach a lot of stuff here. And what would we do on this one? If it's vertically, you do not put the mathematical operation inside the function next to the x, but you put it outside of the function. And you can write it in the front or in the back, it doesn't matter. And you do what it says. When it's vertically, you do what it says. So this is up to, so you would say addition of what?
2.
2. Or if you wanted to, you could put that addition of 2 in the front and write it this way. So these are the same thing. It's like saying 3 plus 2 is the same as 2 plus 3.
What is this you said? Is it vertical dilation you said, or?
No, because it's not being compressed or stretched away from either the y-axis or the x-axis. It's just being picked up. It's this red basic one just picked up and moved up straight. Everything's just picked up and moved 2 units up. So that's called a vertical translation or a vertical shift.
Okay.
And it doesn't help when there's different words that we could use. But does that make sense, Grisela?
Yes, sir.
And I'm having trouble here. William, are you with us? William? I think he ditched us, okay? Okay, so anyway, and look at this one. So Grisela, again, it's at the origin. If you move 1 over, oh, that one does not look like it's 1 down. So this one would have 2 things happening here. See, when you move 1 over and you go 1 unit down, this is 1 unit down, 2, 3, 4, 5. So this is 1 unit over and it's only half. So this actually got, first of all, it got reflected. It took this red basic one and it was reflected over which axis?
The vertical? I mean the y-axis?
Which one is this one?
Oh, the domain, the x-axis.
Very good. So this one has two things happening here. It first was reflected, and I'm just drawing it fast, so it's not accurate. And then it was compressed. The distance, I should have been more careful, but now this distance is now compressed closer to the x-axis. And so this is actually two things, a reflection over the x-axis and then a vertical compression or a shrink, or you can call it a shrink. I should just use one word, but a shrink, okay. That's what this is. And so that's not what this set up on top. So I'm not gonna write down or try to guess what this would be. So that's maybe going a little too far at the moment, but I hope this one is believable. 0, 0, it's still opening up. If you go 1 over, if you go 1 unit over, how do I say this? Let me go back to this one. Remember on this one, if you go on the basic one, if you go 1 unit over and 1 up, you're on the graph. And now we compressed it 1/2 the distance to the y-axis. So this point moved over to like right here. Yeah. And so that's what happened right here. So the point was 1, 1, and now it got compressed closer to the y-axis. So now it went from this dot on the original graph to this dot. And the same thing with 2, 2, 2, 2 was here. And that's right here, 2, 2. And then when you compress it or shrink it closer to the y-axis by 1/2, well, now it moves half the distance and it became this. So, and if you do that, it does look believable that it's on the graph. Okay. I hope I didn't lose you there. So I hope that this one is the only one that is reasonable to believe or to accept. Yeah?
So that would be from where it's 2, it would be up to 4? Because you're moving up to from the original.
Do not remember, that's, yeah, so that can be confusing. But I don't want to say much about that because it might confuse you more. I'll say it later in the class, but
Okay.
this was, Griselda, when you go over 2 on the original graph, then if you go up 2, that's one of the key points, isn't it?
Uh-huh.
It wasn't over 2 up 4, that was the parabola.
Oh, okay.
So what's this supposed to do when you compress it? Instead of being
Half.
it's half of that. So instead of being 2 units away from the y-axis, now it's only how many units?
Half.
Half of that. So it'd just be right here, which is 1 unit away. Yeah?
Yes.
So it's easy to get twisted in our minds here. But so you end up getting, something like that. Okay. Okay, well, so I hope that's okay. Let's go back. And I didn't click this one yet. Click. Oh, and then down here. And then to make things right here, they're just asking you an alternative way . So what did we just do, guys? We took y equals absolute value of x was the parent function. And what did they change it to? They changed it into, they did what? They said, hey, we're going to do a horizontal dilation, which means take the inside next to the x and multiply it by something. And they said, if you multiply it by 2, then this has an impact on the horizontal dilation. And that is, again, to move all these points closer to the y-axis, and not times 2 distance, but the distance divided by 2. So instead of, this is how it's written, which is what they gave us. And another way to write it is this. So instead of f of x equal to absolute value of x, the change is now, what did they do instead of the x right here? They changed it to a what?
A
Division.
division of 2.
Well, that's what we had to do when we did it visually on our graph paper, yes. But what did they do? What's written here? Not absolute value of x, but x times what?
2.
What's the change is times 2, huh? So times 2, that's supposed to be a 2. So, sorry. So this was, okay, they multiplied the x by a 2, and now that's the reason this equation is no longer absolute value of x, but absolute value of 2x. And then you're right, when we start to analyze the graph, then we're supposed to remember, okay, we do the mathematical inverse of multiplication of 2, which is division of 2, and that means take all the points on the basic original graph, and the distance away from the x-axis now, I mean, the distance away from the y-axis now is now going to be a division of 2, or 1/2 the distance that it was to begin with. And but what is the change on the original function? Instead of it being f of x, it now became f of what? F of what?
2x.
2x. So right here we put a 2x. Which then would give us this part, which is what was happening. So here we're just going to type 2x. And let me clear all that. And check. And we are good. Okay. So for whatever it's worth, we're doing the most, in my opinion, the most difficult one. And then from here on, it's going to start to get easier and faster. Okay. So let's try another one. I'm going to let you guys do this one. This is almost like this one. It's absolute value of x. It's absolute value of x, but instead of times 2, it's now times what?
Half.
A half. So first of all, we're supposed to know just by looking at it, by looking at the equation, we're supposed to know, is this telling us to shift the graph of the original absolute value function left or right or up or down? Is it telling us to reflect over the x-axis or the y-axis, which is called, that's a reflection? Or is it a dilation because there's a multiplied numerical effect? Well, clearly it's a multiplication, and that means dilation. And then it's either horizontal dilation or vertical dilation. How do we know the difference? If the multiplication is inside the function, the original function, the original is the absolute value function, then we know that it's a horizontal one. If it would have been out here and out here, either on this side times 1/2 or in front of it times 1/2, it doesn't matter because it's just outside the function, then that's a vertical dilation. So what's this one, ladies? William, what's this one going to be? So it's a dilation, but vertical or horizontal?
Horizontal.
Horizontal. Good. And what are we going to do with all the, what is the inverse of multiplication of 1/2? Or you could say the mathematical inverse of division of 2. So however you want to think of it in your mind, what's the, by the way, when you say the mathematical inverse of multiplication of 1/2, you can also, since it's a fraction, you can just flip it and say 2/1 and say multiplication of 2. Or you can think, oh, this is the division of 2, and the mathematical inverse of dividing by 2 is multiplication of 2. So whichever way makes it feel nicer for us. So what does that mean? Even though this says times 1/2, we're supposed to now know that what are we going to do to the original points of the absolute value graph? Those original points on the, oh boy, on the absolute value graph are now going to be, this is the original. So these key points, 1, 1, I know that's pretty horrible. 1, 1, 2, 2, they're going to do what? They're going to be horizontally dilated, but either closer to the y-axis or away from the y-axis. And how do we know which one? Well, you do the mathematical inverse of whatever it states here. So what's the division? What's the inverse of division of 2? It's what?
Multiplication of 2.
Which means that this point now, which was 1 unit away, is now going to be how far away?
3.
Well, how far? I see what you're thinking, but this is 1 unit away, huh?
Uh-huh.
1 up 1. Let me go to my notebook. So here's the original absolute value graph, which normally is 1 over 1 up, 2 over 2 up, like that. And the same thing on this side. And then the 0, 0. And now we're going to take these points and we're going to, where's my pencil here? And we're going to do what? Yeah, we're going to, instead of divide, the distance is not going to be 1 unit away from the y-axis anymore. It won't be this 1 unit. Oh, that doesn't show very nicely. It's not going to be 1 unit away. It's going to be, what did we just say?
2.
Times 2, twice the distance, huh?
Uh-huh.
So instead of being 1, this point is currently, originally 1 unit from the y-axis. Now it's going to be how many units? Twice that. So what's 2 times 1?
2.
So now it's going to be right here, isn't it?
Mm-hmm.
And you were kind of, I don't know how you were thinking of it. You might have been saying, okay, 2 times 1 is 2 plus the distance it already is, and that gives you 3.
Yeah.
But do you understand the difference?
Yes.
So, okay, so what will happen to this point? I mean, currently on the original function, it's how far away from the y-axis?
2.
2 units. And now we're going to do what to it based on that 1/2 that's been multiplied up here times 1/2 is going to do, what did we just say? It's going to take this, you take this distance from the y-axis and you do what to it?
Multiply it by 2.
So 2 times 2 units is going to be now
4.
4 units. So wherever 4 is here, and you know, I'm just sketching. Okay, so maybe like right here. So this point is now going to move out to this point. This point moved to here. Is this point going to change, guys?
No.
No. And this point right here was how far away from the y-axis? It was how far?
1 unit.
And now it's going to be times
Two.
what? So that's going to be now how far?
-2 unit.
Mm-hmm. So this point is going to move out to this point. This was how far away? This point here, I should say, was how far away from the y-axis? It was how many units again?
2.
So times 2 is now going to be how far away?
-4.
Mm-hmm. And then we get something like this. This point does not change. And then when we connect this, and I'm nervous here, I'm gonna mess it up. Hey, I didn't mess it up too badly. Okay, so it's gonna look like that, isn't it? Something like that. This is supposed to be straight, okay? Griselda, is that making sense?
Yes.
Okay.
So that would be stretching it, right?
That's a horizontal stretch from the y-axis, huh? The distance from the distance of these points on the original absolute value graph are being stretched by a factor of 2, a multiplied factor of 2, or a scale factor of 2, which is why this now opens up more. Yeah.
Mhm.
And so this is this distance from the point away from the x-axis, from the y-axis is being stretched. Stretch means this point, this whole thing gets stretch it out, yeah? And you stretch it by twice the distance that it currently was. Does that make sense?
Yes, sir.
So, okay, so we go back. Go back and to WebAssign. And so, well, we already did this one, so I guess I wasn't going to do it, and somehow I did it. So, Griselda, what was this? This came from what parent function?
Multiply by 2. That, I don't know.
You're right. We ended up multiplying it by 2. But what does this? This was the new equation, but it comes from what original basic graph, or what parent function does it come from?
I'm sorry, I don't know.
Well, it's just like, it was like my notebook. What graph were we looking at that we ended up changing?
Oh, the absolute value.
Mm-hmm. And then didn't it change and they wrote a 1/2 inside, a 1/2 multiplied 1/2?
Mm-hmm.
So that when we look at the multiplied 1/2 times x inside the absolute value, we're supposed to say, oh, this is a changed function, but it really is a changed function that is compared to the original graph, which is this one. Does that make sense?
Okay.
Okay, not really okay.
It's a change function. That's the original function.
Correct. Another name for original is parent.
Okay.
Okay. Because I know you're a parent, Griselda, and your kids always say you're the original mom. Yeah.
Yes.
You are the parent. You're the one and only. Okay. So
it comes from the absolute value
function.
function.
So then we just go over here and we write that. And then we put x in, and that's that. Now, what kind of transformation is this 1/2 again, Griselda? Is it a reflection?
No,
Is it a
horizontal
vertical shift, a horizontal shift, or is it a, or it's a dilation, and what kind? Vertical, stretched closer to the x-axis, further away from the x-axis, or to the y-axis?
It's a horizontal stretch.
Yeah. Mhm. And some authors would write by a scale factor of 2, but they don't make us write that, okay?
Okay.
And now, which graph is it? Oh, so what are we gonna put down here first? What's the change? Instead of f of x, equaling the absolute value of x, that's the parent. Now, g of x, which is the brand new name, really is taking, maybe I should have, g of x which comes from the original parent function f, but instead of x, there's a change. And what is that change, Griselda, on this problem? It was what? Not
Half.
what we, yeah, half.
No.
Mhm. Good. So this right here is a way of saying equals to absolute value of 1/2 times the x. Oh, times the x. Okay. So anyway, so right here, we're going to put that. And times x. I don't know if I got, yeah, I think that's okay. Oh, and now, well, I guess we could check that. And we got this part right, this part right, this part right, and now we just have to match the graph.
It would be A, or the first one.
Yeah, very good. So the original graph would have been inside here, and those points got stretched out away from the y-axis. Is that okay?
Yes.
Megan, is that okay?
Yes.
Okay. So I hope we start, it starts to move along here and it's making sense. And let's go on. I want to come back up this way then. Okay, so how about this one? So Griselda, what's happening? What is this function right here coming from? What was the parent function? This must have come from what original basic parent function or basic function?
From the square root?
Good. So we're going to type square root here. Okay. And then are we multiplying? We are multiplying by a number times 2. But is it inside the function, Griselda, next to the x?
No, sir.
So that means it's not a horizontal dilation, or it's not a horizontal It's not taking the points, moving it closer to the y-axis, or which would be shrinking, or away from the y-axis, which would be a stretch, huh? Not a horizontal stretch and not a horizontal shrink. Is that okay?
Okay.
So if it's not a horizontal shrink or a horizontal stretch away from the y-axis, then because there's multiplication, but it's out in front, it's multiplied by the entire parent function. So this whole parent function is the square root of x, and then that parent function is being multiplied outside by a number 2. So then that means, because whenever you have a multiplication, that means a multiplied scale factor, and that means a dilation. It just whether or not it's moving, shrinking towards the y-axis, stretching away from the y-axis, that's horizontal, or the other dimension, which is up or down, which means the points are either shrinking closer to the x-axis or stretching away from the x-axis. That's a vertical dilation. And so which one is this one then, Griselda? If the multiplication of 2 is not inside the function next to the x.
I would say it's a vertical dilation.
Vertical, very good. It's a vertical dilation. And then when it's vertical, you do not do the mathematical inverse of what it tells us. You do the same. So if we go back to our original graph, the parent square root function. So Griselda, these are the key points here that I just picked. 0, 0, over 1, up 1, over 4, up 2. Yeah?
Yes.
And so when we are given this equation, take the square root function, multiplication, but it's outside of the original function, then that is a vertical dilation, which means you take the original graph take the original key points that I'm suggesting. You could pick other ones, but and then, so here's the key points. And because it's vertical, you are gonna do what it says, and you are gonna take the distance these points are currently from the x-axis, vertical distance. How far is this distance, Griselda, from right here on this point, this point right here, that's over 1, up 1? What's the current distance that it is from the x-axis? What distance is this?
1.
1 unit. And now when you perform this vertical dilation of ×2, you do what it says, not the mathematical inverse. So this distance now is not going to be 1 unit away now. From this point won't be 1 unit away from the x-axis anymore. It's going to be ×2. So you do what it says. So ×2, and which is the scale factor, yeah. And so what's that distance now going to become? Not 1 unit anymore away, but how much, Griselda?
2.
Mm-hmm. And so what do you think that would be called? A vertical shrink or a vertical stretch?
Vertical stretch.
Mm-hmm. So this point right here is going to now become this far away from the x-axis. Is that okay?
Yes.
How about this other? We could do these other points, but I just picked these two. and then this one. So what's this distance right now, Griselda? How far is this point on the original parent function away from the x-axis? How much is this?
2.
And now we're going to multiply that by what?
2.
And it's going to become how far?
4.
4. You understand?
Yes.
And what about this point right here, Griselda? How far is this point right here away from the x-axis right now?
It's a 0.
0 distance. And now we're going to multiply 0 distance times 2. What's that going to be?
0.
So at this point moves or stays?
Stays the same.
And now connect. And it's going to look something like this. And that's this graph right here. Any questions here?
No, sir.
Megan, are we okay with that?
Yeah, I'm okay.
Very good. So we're going to go back to WebAssign. And so now, Griselda, which one of these is it going to be?
Vertical stretch, sir.
Very good. You're very faint, your voice. I can barely hear you. Maybe it's because I'm half deaf. I'm not sure. Now, what about down here? What was the change right down on this function? And that kind of seems peculiar at first, the way they write this. So didn't we start out with the original function f of x? That's the parent function. And it's the
Yes.
square root function like this.
Yes, sir.
This is the parent. Now we're doing a transformation, in particular a dilation. And so here is the new graph, which is not the basic parent function anymore. It is, so it has a new name. This one's the new one, the one that we're being asked about. They're not going to ask us all day long about the original one, because that would not be very interesting, because then we wouldn't be able to learn these dilation effects. So the new graph is
2 on the outside with the square root of x.
excellent. You take the parent function and you do a change with it, and it's a multiplication effect, and it's outside times 2. And that's the same thing as saying 2 times
Square root of x.
good. Instead of this green f of x, we could just replace this as this. So this right here is the same as this right here. It's just one less step, and it looks kind of abstract at first, but I hope that is okay. So what are we going to put right in here? It's the original function multiplied, but not inside the x, but outside. So all we have to put here is a what?
2.
2. Great. And we can check all of that. Correct, correct, correct. And now match. Griselda, which one do you think is the correct one here?
It would be the first one again.
So the first one, okay. Because when we go 1 unit over, instead of being 1 up,
It's 2.
it's 2 up, huh? Now you're getting it, which is great. Yeah. And now and when we're 4 over, the basic one was up 2, and now it's supposed to be times that by 2, so that's 4. And does this look like it's reasonable to believe that it's 4 up here?
Yes, sir.
Excellent. Megan, any questions there?
No.
Okay, now we're starting to get some momentum, yeah? Which always feels good, I hope. And what am I doing here? I want to check. Okay, and is this the one we just did? Yeah. So, and we matched it and we're good. There's the green check, but that means the one we picked is the correct, not this one. Okay, any questions here, ladies?
No, sir.
No.
So, okay, so if we look at this one, and Megan, of course, which one is this coming from? What this right here is coming from, it's just a slight transformation, a slight change is being done to what parent function, of course.
The square root of x.
Mm-hmm. And Griselda, if you have a question, ask, okay?
Yes, sir. Thank you.
And what is this right here then, Megan? Is it a addition or subtraction either inside the parent function or outside, which would be a horizontal or vertical translation, which is also called a shift? It's not a reflection, which is a multiplication of -1 somewhere, which we're going to go over in a few moments more, but it's a multiplication of a number. And it's either inside the original function times the variable x, or it's not, or that means outside the original parent function. So clearly this number is being multiplied where, Megan? Inside or outside?
Outside.
And that means it's what kind of dilation? Horizontal or vertical?
Vertical.
Vertical, and which means if we look at the parent function, the square root function, and here it is again, then we're gonna pick key points. And if someone else was teaching this, they might have picked the same key points, and they may not have, but if these are the most logical, so probably they would, because that's the beginning. 1 over, 1 up is easy to recognize, and 4 and 2. So anyway, these other points are like 2 over, and then 1 point something. That's not so easy. So, okay, Megan, so what are we going to do if it's a vertical dilation? We're either going to, these points right here are either going to move closer to the x-axis or away from the x-axis, which is a vertical stretch or a vertical shrink. So it just depends on where is the multiplied number. And what and where was it, Megan? Inside or outside?
Outside.
Times what number?
1/2.
1/2. And when it's outside, it's vertical. And when it's vertical, do we do the mathematical inverse of what it's telling us, or what, or not?
You do what it says.
We do what it says, which means what then, Megan? The distance that these points are away from the x-axis are going to change by a factor of this. And so what does that mean? This distance, what is this distance right here again, Megan, right here?
1.
Good. 1, that's, oh well. 1 unit, and now it's going to change. And this was how many units away from the x-axis?
2.
And these distances are going to change because there's a multiplying effect, and it's by 1/2, and you do what it says. So what's 1/2? What's 1 unit away from the x-axis times the scale factor or the dilation factor of 1/2? So what's 1 unit times 1/2? It's going to just be what?
0.5 or 1/2.
Mm-hmm. Which means what?
It's
Megan?
gonna shrink.
It's going to shrink, right? So now you go from the x-axis, and it's only 1/2 a unit away. So now this point moves down to this one. I mean, this will become, this point now moves 1/2 the distance, and on the new graph, it's going to be right here now. And this point also is going to shrink by 1/2.
So it's gonna move to 1.
Good. And that equals 1. And that's the distance. That's the distance that, so if you come down here and you go 1 unit away, 1 unit up, that's where this point is now on the new graph. It's going to be right here instead. So what are these? What is this kind of dilation, Megan? It's vertical, but is it stretching away from the x-axis or shrinking?
Shrink.
So vertical shrink. Is that okay, Griselda?
Yes, sir.
Okay. You didn't go have a lemonade in the backyard, did you?
No, I'm just sending a text message to my son's therapist.
Okay. So now if we connect these points, we kind of get an idea of what's going to happen. Oh, I forgot to mention, Megan, or ask you, what about this point? How far is this point right here, right currently on the original function? How far is it from the x-axis?
It's at 0, 0.
So it's 0 units away, huh?
Mm-hmm.
So if you multiply that by 1/2, is that going to change?
No, it'll stay at 0.
Good. Okay. So now we come back to our WebAssign. And so which one of these is the correct one then, Megan?
Vertical shrink.
Mm-hmm. And what about down here? So we're going to take the original function, which was the square root function, and we're going to do something to it, to change it, to transform it, and we're going to call this new function, say it's g, that's what they told us, and it is created by taking the original function f of x and doing something to it. Are we going to add or subtract something inside the x variable, which is inside the function, which would be a horizontal translation or shift? If it was addition or subtraction outside the function, either at the end or in the front, that would be a vertical shift, vertical translation. That's not it. We're not multiplying the whole function by a -1 outside or a -1 inside. So it's not a reflection over the x-axis or the y-axis. It's a multiplication of a number, which means dilation, but it is where, Megan? Inside next to the x, inside the function, which would be a horizontal dilation, or is it outside the function?
Outside.
Outside, and it was times
1/2.
And if we wanted to, we could go one step further, although this is, they wanted us to stop right here. That's what they want down here. But if we wanted to, we could go one step further and change f of x to what, Megan? What is the original function? What was the parent function that this all came from?
The square root of x.
So this is our new function that they gave us in the directions. It comes from the parent function, the square root function, and something was done to it. So something is done to the f of x, and it's multiplied by 1/2. And this is what they want down here. So use function notation, which is the g of x and the f of x, to write g, the brand new function, in terms of the parent function, f of x. So here's the parent, and then we make the change, which is a multiplication of 1/2. Any questions here?
No.
No.
Okay, so I hope that's getting easier and easier now as we do it, yeah?
Yes.
And so we type a multiplication, well, we don't have to write the multiplication, just 1/2, because right here is the times. And check that. And correct, 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 and now match. So it can't be this. By the way, what would this be right here, do you think? Here's the original one, because we're about to talk about them. What am I doing here? Here's the original square root function, over 1, up 1, over 4, up 2. Ooh, well, I guess they made it more difficult than I was thinking they would have. Here is y equals square root. And they first reflected it over the y-axis, so that would be a reflection. And that means multiplied by a -1. And we're going to talk about that more formally, but when you reflect over the y-axis, you multiply inside by a -1. But they're not asking us this here. And not only that, then it's also compressed. And then we would also then have to multiply. This looks compressed. Instead of being 1 unit up, right? If you go, oh, I'm sorry. If you go 1 over, 1 up, 1 over, this doesn't look like 1 up anymore. It looks like half. It's kind of hard to tell for sure, huh?
Yeah.
But it might be a half or a third, and then it would be in the front here, like a 1/2 or something. But anyway, that's going too far. That's not what we need to concentrate on right now. But anyway, so, and this one would be a reflection over the x-axis, and also compressed closer to the x-axis. So that's not it, because all we're doing is taking this one and compressing it only. So which one is left? It's either this one or this one. So that's why we,
First one.
the first one, good. Because this one is, oh, wait a minute. This one's 1 over and not 1 unit up, which is the original square root function, but it's stretched further away. And so that's not it. This is over 1. The original one is up here at 1. This is a 1. And it's the original one's here. And 4 over up 2 is the original. And this point right here did compress closer to the x-axis, and so did this one. Yeah. So does that look reasonable, ladies?
Yes.
Yes.
Okay. So clear. Go back and click this one. And check. And we hopefully are correct. Yes. Okay. So hope we're hanging in there. So we've done the most difficult part of all this. And I know we're getting tired now, but now it starts to get faster and faster. So these down here, let me just scan. Okay. So not to intimidate, they look a little scary, but so now I want to cover the reflection, the two reflections, and then all we have left is the translations, which we've already done numerous times, and we've done reflections, just not as often. And then we put it all together, and that'll do it. So let's see, do I have any here? I want to. Okay, so sorry, I'm going to show you at Desmos two things here. And I'm just going to pick one of the original parent functions. And how about we pick the square root one, since I think that's a nice one that illustrates it all. And the square root of x. Okay. Now, now we're going to talk about the reflections. There's only two that we have to worry about or learn, and that is reflecting the original equation about the y-axis. Okay, so for example, to try to make it understandable, I hope, for example, this is the square root graph, and this is one, that was a key point, remember, on my notebook. So, excuse me, so 1, 1, and 4, 2. So if we write down this point, 4, comma 2, x comma y, then what would happen to this point right here, ladies? So hang in there. This is really the last little tiny thing here that has a little bit of complexity, is that if we want to reflect this over the y-axis, this axis right here, then I could have just done this, but anyway. Then this point is, how far away is this point right here to the y-axis, Megan? How far is this point to the y-axis right here?
4 units.
Good, and so when you reflect it over the y-axis, it's just going to be instead of 4 units away from the y-axis to the right, it's now going to be 4 units to the left of the y-axis over this way. So I hope you ladies can understand this point. When you reflect it, it's like you pull it out in front of you and it swings out towards your face, and then you put it back down over here, and that reflects. So from here over, from here over to here. Is that okay?
Yes.
And Griselda, what point would this be right here? not 4, 2 anymore.
Negative 4, 2.
Mhm. So the 2 stays, the 2 over here stays the same. The 4 kind of stays the same, but times what in front, Megan?
-1.
Mm-hmm. Sorry. I'm getting dizzy here pushing all these buttons. Yeah. So instead of 4, 2, the 2 does not change. The 4 is kind of the same, but it's simply multiplied by a -1. And that becomes -4, 2. So the same idea for any other point. I wish I could just right here, over here is 9, 3. And if I slide this, then all this, my scribbling is going to get messed up. But right here, right there is just a tiny bit more is the 0.93. So if we take the point, let's just pretend it's like right here, and it's 9, 9. The square root of 9 is 3. X comma y. And what's going to happen to this point when you reflect it? How far is this point, Griselda, away from the y-axis? How far away is it right now?
9.
And so when you reflect it over the y-axis, it's just going to be how many units over here?
9.
9.
-9.
Mm-hmm. So what's going to happen? What's going to happen to that point 9, comma 3? What's not going to change?
The 3.
Mm-hmm. And even the 9 part is not changing. But what is changing? A times
The
what?
sign. -1.
Yeah. So it has a multiplication of -1 on the x variable. Yeah, this y is the same as over here, and this x is the same as over here, but times a -1, if that makes sense.
Yes, sir.
So, and the same thing happens with all the points. This is 1 unit over, and now it becomes -1. So this was 1, 1. And now this is still 1, and now it's 1 that it was, but times a -1, which gives you -1, 1. This point right here, how far away is this point from the y-axis, Megan?
It's at 0.
So there is no distance, is there?
No.
So when you reflect it over the y-axis, it's not like, oh, this was 1 unit away and now it's going to be -1 unit. It's no units away. So when you reflect it, it's still going to be 0 units away. So does this point move or stay the same?
Stays the same.
Mm-hmm. And what will happen then if we try to connect these points? Well, you get the reflected graph, which is the brand new one.
Looks like a seagull.
And good. And now the question is, what is this equation? Well, doing what we kind of wrote before, if the original equation, the parent was the square root function. Then the new equation, hang in there, is g of x. This is our new one. And the original is the parent function. This is supposed to be an e. And what do we do to the parent function? Well, we did something to the function, and we're not adding or subtracting inside next to the x. That's a horizontal translation. It's not addition or subtraction outside of the function. That would be a vertical translation. It's not multiplying inside the x by a number. Well, it is by a number, but it's -1 is the special case. So, it's not like a ×2 or a ×1/2 or something. So it's not a horizontal dilation. It's not a multiplication outside of the function, like a ×2 or a 1/2. So it's not a vertical dilation. It is the x values are all multiplied by what? By a negative what?
-1.
And so here is the change right there. The new function is the original parent function times, and inside next to the x is a times -1. And this is when we have a reflection over the y-axis. Reflection about the y-axis. So every single time we reflect about the y-axis, this is what's going to happen. Yeah, you take the original parent function, and inside next to the x, you multiply it by -1, because that's what happens when you take points and you reflect over the y-axis. These x values now become the same x value, but multiplied by -1. And the same thing, by the way, if the graph originally was on this side, then when you reflect it and it goes on the other side, it's the same thing. The x values will now become on this side, which is the same thing as saying multiply by -1. So, so our g of x could be written as, so this is correct. So the author is going to ask us to do this, but it's also correct to say, take so you take the -1, oops, getting my colors all confused here. -1 times x, and that is inside the original function. So, and if we look at Desmos, oh, I'm on Desmos, what am I talking about? If we take the square root function, and which is this one, and multiply it by a -1, we should get this reflection of this original one. And there it is. Okay. Any questions here?
No, sir.
No.
And then the other kind of reflection is not over the y-axis, but over the x-axis. So there's only two reflections. And that one would be, we take these points right here, but reflect instead over the x-axis. And this one here. Pretend that's 9 over there. And this one here, all of them. These are just some key points. This one, it's really already on the x-axis, so when you reflect over the x-axis, it's not going to move. It's going to stay here again. But how far, Griselda, is this point right here? How far is it away from the x-axis? It's how many units?
2.
2. We're not going to shrink it or stretch it from the x-axis. That would be a vertical dilation. We're going to reflect it over the x-axis. So instead of being 2 units above the x-axis, now it's going to be what, Griselda?
2 units down the x-axis?
I can barely hear you, Griselda.
2 units down the x-axis or below the x-axis?
Good. So it's going to be right here, isn't it?
Yes, sir.
And same as this one was, how many units was this point right here above the x-axis?
3.
And so now it's going to be how many below?
3.
3. If I can draw this straight. And this one was 1 unit above, so now it's going to be 1 unit what?
1. Negative 1.
Good. And now we could do another 1,000 points here if we wanted to, and if we did, and connect them, then we would get something like this. Oh boy.
Looks like a parabola.
Very good. And it actually is a parabola if you combine both pieces. But this part is the reflected one. So this one is the new graph, g of x. It's the new one, the reflected one. And it's equal to the original function. Hang in there, we're almost have all our translations because we already know about, all our transformations, because we already know about shifting left and right or up and down. And so what's done to reflect? Well, what happened? Oh, by the way, Griselda, what does this point now become? So it was
9, negative 3. Oh, I'm sorry. I'm looking at the wrong one.
okay.
4, negative 2.
So did the x value change, Griselda?
No, sir.
But the y value changed, didn't it?
Yes, sir.
It went from, the x value is still 4, and the y value is still a 2, but it's 2 times what, Griselda?
2 times negative 2?
Negative. So if you multiply,
Oh, no, wait.
if you multiply this 2 by times negative 1, what do we get, Griselda?
By negative 1, it would be negative 2.
Very good. Thank you. Which is what this is down here. Isn't this now 2 points below the x-axis right here?
Yes, sir.
And what about the 9, 3?
That would be 9 stays the same. Then you will multiply the negative 1 times the 3.
Very good. So I'm trying not, I could just say, this is what it is, memorize it, and so be it. That would take a lot less time. But I'm trying to give everyone an opportunity to really understand it, and then it can be really nice. It just takes a long time. So negative, you reflect over the x-axis, and what's going to change? Not the x value,
The Y value.
the y value. And what is the change? It is the original y value times -1.
1.
And so if we do take the original y value 3 multiplied by -1, we do get, I just rewrote, I already had here, sorry. And that gives us 9, -3. So what I'm trying to say is, and the same with this one, what I'm trying to say then is when we reflect over the x-axis, or about the x-axis, or then the new function if we call it g for Griselda, I mean g for the new function, it's equal to the original function. And remember, all this was f of x equals square root of x, this original piece, this one up here. And so we take the original function and what do we do, Griselda? What happens to the original function? What part changed? The x value, like it did on the reflection over the y-axis, we had to multiply the x value times -1, and that multiplication of -1 was inside the function next to the x variable. But that's when you reflect over the y-axis. What about when you reflect over the x-axis? There is no change on the x value, so there's not going to be a multiplication of times -1 inside this function. But what is being multiplied by -1, Griselda? The x value or the y value?
The Y value, sir?
Very good. Another name for the y value is the f of x value. So what happens to the y value, which is your mapping, your range value, or your f of x value? It is the same number, but times -1. And that is outside of the function, which we can write whatever color, and we write it outside. It's times the y value, and this is the same thing as a way of writing the y value. So here is, for any reflection over the x-axis, the new function is going to be the original function, the parent function, times -1, but not inside the function next to the variable x, because that would be a reflection over the y-axis. It's a multiplication of -1 outside the function, and which is the same thing as saying the y value you multiply by -1. So in this case, then g of x, this is one way to write it. And in this particular case, we would write the -1 multiplied by the original parent function, and the original parent function on this one is the square root of x. And excuse me. So I know that's a lot of stuff here, but we made it, I hope, through all this. And so if we graph that, take this equation, copy it, but multiply that purple equation that just turned red because I just put it again, but now multiply it outside by a -1 in front, and this purple graph is going to reflect down to this scribbly graph I have, but be cleaner. And so presto, and there it is. Yeah, so there it is. Any questions here, ladies?
No,
Sir.
Megan, are you hanging in there?
I am.
Okay, so now that takes care of all the things that we need, and now it's just a matter of practice. So let's see here. Go back and clear. Okay, so how about number 1, Megan? Can you read that for us?
Oh, hang on. Let me let my dog out really fast.
Oh, it's okay.
Hang on. Okay. A reflection in the x-axis of the graph of y equals f of x is represented by h of x.
So instead of g of x, they just wrote h of x. And what happens when we reflect about the x-axis? That's the one we just talked about. And so what do we do to the original parent function when we reflect over the x-axis? It's a multiplication of -1, but where? Inside next to the x or outside in the front of the function?
Outside.
Outside. So right here, it gives us these two choices. And Griselda, which one is it then? The first one or the second one?
The second one, sir.
Mm-hmm. And then Megan?
While a reflection in the y-axis of the graph of y equals f of x is represented by h of x.
And then again, reflection, multiplication of -1, but Megan, where are we going to have that multiplication of 1 when you reflect over the y-axis? Outside the function or inside?
Inside with the x.
Excellent. And that would be the which one? The second one?
Yes.
Okay. And we're good. Okay. This one right here, it's just a fancy way of, non-rigid is a fancy way of saying the shape of the new graph is not going to be identical to the shape of the original one, because, and the only time that's going to happen is if we do a dilation on it, because it gets compressed or it gets shrunk, it shrinks or stretches either away from the y-axis or from the x-axis. So this is a fancy way of saying the graph is not going to look the same anymore precisely than the parent function, because it gets either stretched or it shrinks. And so that's what they're saying here. And here's one of them. And Megan, which one is it when we multiply the function by a number and it's not multiplied inside next to the x, but it's multiplied outside? And it's not talking about c being a -1, because that's a reflection, just any other number. So which kind of what kind of dilation is this one when we multiply the number not inside next to the x, but in the front of it?
Vertical.
Vertical. Good. And then they gave us two choices here. Stretch or shrink. Well, it depends. It says right here, when c is greater than 1, So give me a number greater than 1, Megan.
3.
3. So what happens if this was a times 3 in front? Yeah. And when it's outside and it's vertical, do we do the mathematical inverse of multiplication of 3 and say divide by 3? Or do we do what it says when it's vertical and it's outside?
You do what it says. So it's going to stretch.
Very good. So if C is greater than 1, that means it's going to stretch. Good. And what is this part? What's a number between 0 and 1, Megan? Give me a fraction that's between 0 and 1.
1/2.
And so what's going to happen when that's the kind of the situation? When that's a 1/2 in front, then it's still vertical. You still do what it says, not the mathematical inverse. So it's not going to, so it's going to be a what? A vertical.
Vertical shrink.
Very good. Okay, so this goes over translations. And so let's do these real quick. So again, well, let me do this maybe. So look at this one, x squared plus 6. If I go back to my notebook, x squared is the parabola. It's not this bluish one, but the original one. And if we shift it left or right, or up or down, that's a translation. And if it's inside, maybe I'll do it this way. Sorry. Y equals the square root of x, x squared. There's the parabola. And if we make a change, and the change is y equals x squared plus 6. And I need to move this down. So whenever you add or subtract, either if it's inside the function, here the addition or subtraction is inside the function next to the x variable. When that occurs, then it's a horizontal, x dimensions horizontal, and you do what it says. So it's this, you do the opposite of what it says because it's horizontal. So this is the original one. And you notice 0, 0, 1, 1, negative 1, 1, 2, 4, like that are the original points. And all this graph is just moved over to the opposite of the mathematical inverse of addition of 6, which is subtraction of 6. If the addition or subtraction is outside of the function, not inside next to the variable x, then it's the vertical translation. And then you do what it says. So plus 6 would be up 6. And that's what this green one is right here. Any questions there, ladies?
Can you repeat the last part, please?
When it's outside?
Oh, no, the last one, the third one.
This one?
Yes.
So where is the addition or subtraction of in this case, a 6, Griselda? Is it outside of the parent function x squared, or is it inside? Let me put a little parenthesis here. That kind of helps.
Okay, it's outside, sir.
Yeah. So, so it's, no, this one, the green one is outside, isn't it? The addition of 6 is outside of the x squared.
Yes,
Uh,
sir.
But on the purple one, the addition of 6 is inside the function, isn't it?
Oh, yes, sir.
Does that make sense?
Yes.
So what kind of change, what kind of translation or shift does this one, Griselda? If it's inside the function next to the x, is it with respect to the x dimension, which means left and right? Is it with respect to the y dimension, which means up and down? Which one is it?
We would move it up.
If it's inside next to the x, you move it left or right.
Oh, okay.
And you do the opposite of what it says. So what's the opposite of plus 6? What's the inverse, mathematical inverse of addition of 6? It's what?
-6, sir.
So that means it's going to move the original blue graph and just literally take this blue original parent function and slide it or shift it or translate it 6 units to the left.
Okay.
And do you see how this point moved 6 units to the left? And so does this one, like right here. This one moved over to right here like that.
Yes.
Is that okay?
Yes.
And so what happens when you add or subtract, but not inside the parent function, but outside? And you could write +6 at the end of the equation, or we could write it this way. So these two are the same thing, it's just switching around, but it's still addition of 6, but outside of the function, of the parent function. So then what does it do, Griselda? Is it gonna shift it or translate it left or right horizontally, or up, down, vertically?
Up and down. So it
And
would
you
be
do the
up.
opposite, or what it says?
No, I think it would stay the same.
So you do the same, yeah. You would pick it up, you'd move it up +6 units, which is this green graph, isn't it?
Yes.
Is that okay?
Yes, sir.
Boy, I was lucky. I have green here, and I have green on my pen, and I was just by luck there. So anyway, I think I'm losing it. But so having said all that, now I hope when we go back to this, Griselda, so same kind of things we've done on the other questions. What kind of what's this coming from? What's the parent function that this new equation is coming from?
From y equals x squared.
Good. And sorry, where am I at? I don't see it. So, oh, this one, square. And what kind of transformation? Transformation is the general name for any kind of change to the parent original function. So we have translations, left and right horizontally, up and down vertically. We have reflections over the y-axis, over the x-axis, and we have dilations. So which are vertically or horizontally shrinked or stretched. So which one is this one, Griselda? If there's an addition or subtraction, it's a translation, and it's either horizontally or vertically. And which one is it if the, in this case, it's addition, but it's not inside the x squared, it's outside?
Would it be vertical shift 6 units upward?
Very good. And then, so which one of these parabolas does it have to be then, Griselda, if you just pick it up 6?
The first one, sir.
The first one, yeah. And notice this is 6 up. And notice still, I know it's not so easily visible, but on our original parabola, x squared, if you went over 1 unit, then you were supposed to be able to go up 1. and that still preserved its shape or its rigidity. There's that fancy word, rigid, non-rigid transformation. The rigidity or how this form looks, it's still, once you're at the vertex point, this key point, you move over 1 unit and you move up and you're still on the graph. And the same thing to the left 1 and it goes up 1 like that. Anyway, so these have changed. These have changed. If you go 1 unit over, well, I don't know, maybe the perspective. Okay, they're messing with us here with the perspective because the scales have changed. But anyway, this one is the correct one. And now down here we do this, I hope it's not so abstract anymore. And just to go faster, we're gonna change, do we change the inside of the function, Griselda, here or outside? Maybe I was too fast. What if we write the original function is f of x equals, what was the original one, Griselda? What's this parent? It was x what?
X squared.
And the new function, g of x, this is the new one that they gave us. And it's equal to the original function, which is the parent function, f of x. And now what change was done to the parent? There's all kinds of possibilities, yeah. But what was the change on this one? Was it, there was an addition of 6, and where was it, Griselda? Inside the function next to the x, and we should write x plus 6 here, or outside of the function?
Outside, sir.
So plus 6. Is that okay?
Yes, sir.
So right here, we're gonna put right here, f of what? This part didn't change, so this is f of what?
X plus 6.
And then what's out here? Plus what?
6.
And notice they didn't write plus 6 afterwards like I did up here, but it's okay to put the plus 6 in the front, isn't it?
Yes, it means the same.
Any questions here?
No, sir.
No,
Megan, you okay?
I'm okay.
Okay, so, and now x and 6. And we're correct up there, correct on the graph, and correct on the bottom. Okay, so I'm assuming now that this would be a fair thing for you guys to be able to do. The -2 is an addition or subtraction, so that's a translation or a shift. And is it inside next to the x, or is it outside?
Outside, sir.
Outside.
Which means what? Horizontal or vertical?
Vertical.
Vertical, and you do what it says when it's vertical, so that means what? Shift vertically up or down?
Down 2.
Down 2. Is that okay, Griselda?
Yes, sir.
So there's problems like that. Okay, so what we're gonna do is, because we're taking so long, is I'm gonna say, well, really I've taught you everything. It's just a matter of putting it together now. So let's do just one more, and then I'll say maybe these problems after a certain number, you could wait until Thursday or try it yourself. But let's do one more, and then we'll stop. And let's do this one here. So 16. So now we have more than one operation, mathematical transformation going on here. So let's look at them. So first of all, Megan, where is this function coming from? What parent function? So that means you kind of like
X squared.
x squared, good. You block out the 4, you block out the subtraction of 2, and you block out this minus sign right here, which is really like a -1. So that's really, in our minds, we need to think of this as -1 times the function. So this comes from x squared. Is that part okay, Grisela?
Yes, sir.
So here we're going to put x squared. Okay. And then, so maybe I'm going to try this. Oh. So the original function is f of x. And what did we just say that was, Griselda? X what?
Squared.
And then the new function, so this will be the last one we do. So I know we're all getting tired. I am too. The new function g of x is going to be the original function f of x,
Plus.
and I'm going to open this up to give more room because, so I'm going to put x here, but what things, so three changes are made here. So first of all, what about any changes inside the original function? Inside the x squared. So here is inside the squaring function. And what's being done? Is there a multiplication of -1 next to the x inside, which would be a reflection over the y-axis? No, I don't see a multiplication. I see a multiplication of -1 outside. That is a reflection, but outside is over the x-axis, not inside. So what else is there? What else could be in here? A multiplication next to the x inside, that would be a horizontal dilation, which is the points are shrink closer to the y-axis or stretch away from the y-axis. Well, there's no multiplication of 2 or 1/2 or a 3 inside next to the x. So it's not a horizontal stretch or shrink. What is being done inside? An addition or a subtraction, and it's a subtraction of 2. So whenever there's an addition or a subtraction, that's a translation or a shift. And you do, so it'll be the opposite of what it says here, or the mathematical inverse of what it says. So that'll be 2 units to the right. But what is being done to the x? It is a subtraction on the x. So that part is a horizontal translation of what, Megan? 2 to the left, or do you do the mathematical inverse of subtraction of 2?
The inverse, so it'll go 2 to the right.
2 units to the right. So we have to work inside the function and then move, and once we've done whatever change is there, then we look outside. So the first thing that is done is move it 2 units to the right, or a horizontal translation of 2. Is that anywhere? So obviously, which one of these is that?
Last one.
So here's the first. This is the first thing that's being done first. Now, what's the next thing? Well, there's nothing left that's being done inside to the original function. This is the only thing. So the rest is outside. And what is being done outside? You look to the closest thing first. What's the next thing closest to this original the squaring function here? There's a multiplication of negative what?
1.
1.
Negative 1. If that's confusing and you say, well, isn't it just subtraction? Remember, this can be written like that plus 4 in the front of all this could be, we could rewrite it like this. And then plus 4. So this is the same thing as this. And it kind of helps perhaps if you move it over to the out here afterwards instead. Is that okay?
Yes.
So then what's the next thing being done next to the original function, the x squared function? This was the first thing done, the horizontal translation 2 units to the right. What's the next closest thing done to this function, this squaring function, is either addition of 4 or multiplication of negative 1. And what do you think we should say the next thing is? What's still right next? Yeah, this is the next thing, the second thing. So the second thing is a multiplication of negative 1. So that's going to go right here. Multiplication of negative 1. And it's not inside next to the x, it's in the front. And what, so we know it's a reflection because there's a multiplication of negative 1. And, well, there's only 2 choices. Reflection about the y-axis or the x-axis. So now you got to think about it. I mean, we could look at our previous work, but I hope we can remember or think about it and rediscover it. And what did we say, Griselda, happens when you reflect over the y-axis? The y-axis. What did we say happened? We had a point like, oh, whatever it was, 4, 2. And what happens when you reflect this point over the y-axis? What happens? What kind of change is it? What happens to the point 4, 2 when you reflect it over the y-axis? It becomes what point, Griselda?
It moves to the left.
To the left. So instead of over 4 up 2, it becomes what? Instead of 4 units this way, it's 4 units this way. And so what changes here?
The x-axis, negative 4.
It becomes a multiplication of negative 1. You remember?
Yes.
So in the y value does not change.
Yes.
So what happens when you reflect over the y-axis? What is being multiplied by the negative 1? Is it the y value, Griselda, or the x value?
X value.
So the multiplication is, if it was right next to the x, if it was right inside, then that would be a reflection over the y-axis. If it's outside the entire function, that's when you reflect the y value. So this point reflects, when it reflects over the x-axis, that's when you multiply the y value by negative 1. So that's what's happening right here. This entire, up here, the entire original function, the parabola, the x squared function, is being multiplied outside by a negative 1. So that's when you multiply the f function, the original function, times negative 1. not inside, but outside.
Mm-hmm.
Is that okay?
Yes.
And then, so that's the second thing. Reflect over the x-axis. So this is the second step. Second step. So this one. And then the third thing is if there's any addition or subtraction outside of the function. And there is right here. It's also, they wrote it in the front. So what's this called right here, Megan? When you add or subtract, that's a translation. And if it's inside the function, that was this one. That was the horizontal one. But this one is outside, so it's not a horizontal shift. It's what kind of shift?
It's a vertical.
Very good. So then it's +4 outside, and that's the vertical shift. The vertical, and what do you do when it's vertical, Megan? Do you do the opposite, the mathematical inverse of that, or what it says?
You do what it says. So it's gonna go up 4.
Mm-hmm. And so, so here is the way to write it. But they might have wrote the +4 not afterwards, but in the front, huh?
Mm-hmm.
So let's look down here at the bottom and check. So let's see here. Yeah. So they have this box here in the front instead of afterwards. So this is going to be the place where we put the what?
The 4.
The 4. And then what's going on in front of the function? That was the multiplication of -1. Yeah, that was this part. But what's being done inside the function? We're doing what to the x?
Subtracting 2.
Mm-hmm. So that's this part. And now I kind of have a mess here, but now we look at match the graph. And so let's see here. Oh, so I forgot, we got to click these. So what was the first thing we said that was going on here? This was a shift of horizontally 2 to the what?
The right.
Right.
Mm-hmm. The multiplication of -1 by the entire function, the original function, the f, or the x² function is the reflection over which axis?
The x-axis.
And then this addition of 4 that they wrote in the front, it could have been at the end, is a vertical what?
Vertical shift up 4.
Mm-hmm. And that's that. And now we want to match the correct graph. So 2 units to the right, and then reflect it over the x-axis. So what's going to happen, here's the original, x². Move it 2 units to the right. That's going to be the x -2 part. Then reflect it over the x-axis. That's going to be this part. And that is this x -2. That was the horizontal 2 units to the right, but multiplied by a -1 in the entire front. And then the last thing was 4 units up. So now I'll take this red graph and move it up 4 units. I know maybe don't have a very good graph here, but very good picture. And that would be the whole thing then, which is the x minus 2 squared times the negative 1 and then the plus 4. And we can write the plus 4 afterwards or in the front. So we're looking at the green graph, which then has to be doing downward. And, oh, what did I say? Oh, yeah. So it has to be opening downward, which is not these two. So it's one of these two. So which one does it look like, ladies, here?
The one on the left.
The one on the left, yeah? Is that okay, Griselda?
Yes, sir.
So we click this one, and hopefully we have it, yeah? And check. And we have it. Any questions there?
No, sir.
No.
Okay, so I know it's been a long time, 3 hours or a little less, but anyway, so I hope that you all can have a very fair and reasonable chance from the beginning of the homework. Let me just take a better look here. So like this one, ladies, they want you to say, okay, what does it look like this graph right here would be? So this comes from the parabola, the x squared as the base apparent function. And remember, if we go back and you'd have to go back and look at my original graph or remember the key points. On the parabola, you go over 1 unit and go up 1, and you should be on the graph. If you go over 2 units, you should go up 4 and be on the graph. So this is 2 over 1, 2, 3, 4, and you're back on the graph. Same thing on the left. 1, 2, and then up 4. So then that means the rigidity, the base, the shape of the parabola has not been changed. It hasn't been dilated. So there's no horizontal shrink or stretch or vertical shrink or stretch, which means no multiplication of a number inside the x or outside of the whole function. The only thing that's happening here is that this parabola did not change its rigidity, its form. It's just been moved down 1 unit. So then to write the equation, it shouldn't be that difficult. We would just write x squared still. And Griselda, where is the change going to be if we move it down 1 unit? That's a vertical change. Is that inside? I got to put a parenthesis in here and put the plus or minus 1 inside the function or outside?
Outside.
And do I write the opposite or do what it says?
Do what it says.
So it's down how much? How many units?
1.
So we should put what outside the function here?
-1.
And then check. Does that make sense like that?
Yes, sir.
Okay. So what we'll do is, so I hope you have a reasonable chance at doing these. if you have any trouble, we can go over some more on Thursday. And you might, maybe you'll have some trouble here, I don't know. But if so, then just bypass these problems and then go starting on 12 and onward. So if you have any trouble on 11, 10, 9, 8, 7, 6, I know it's like, oh my God, 4, well then wait on it and skip to starting with 12. And all of this we've done, that's where we spend almost all of our time. So 12, and we did many of these, and up to 18, 19 is when we did the dilations, 21, 22, and when you get past that, then there's multiple transformations going on right here, and you just got to figure out the same idea. And so try those. I mean, I hope you could get this, for example, just by looking at it. What's this inside called? If you're subtracting 1, is it, which one is this kind? When you add or subtract, it's a shift. Which kind?
Hello?
Is it, if it's inside,
Absolute
is
value?
it's the absolute value function, good. And what's the -1 do to the original graph?
The
Is it a,
opposite?
it's a shift? And do you do what it says, 1 left or the opposite?
The opposite.
So it'd be 1 to the
Right.
right. What's this multiplication of 3 called? When you multiply the whole function in front by a number that's not -1, because that would be a reflection. What is it called when you multiply by a number that's a dilation? And is it inside next to the x, which is a horizontal dilation, or is it outside the function, which is a vertical one,
Outside.
which is a,
Horizontal.
so outside is the
I'm sorry, vertical.
vertical, which means either the points are stretched away from the x-axis or they shrink closer to the x-axis. Yeah?
Mhm.
And so this is going to be horizontal shift 1 to the right. This is a vertical, and it's either a shrink or a stretch. Which, when it's a vertical, do you do the mathematical inverse of it, or do you do what it says?
What it says.
And times 3 would be 3 times the distance away from the x-axis, up or down. So that's not a shrink, it's a what?
To the right. I mean, up.
It's a stretch, yeah?
The stretch.
And what's the +2 outside the function? It's a shift. And is it horizontal or vertical when it's outside the function?
Vertical.
So, and you do what it says, so vertical shift upward of 2, like that.
Yes.
And then you try to match it. So, okay. So, this is a big section, and I don't know how well we're understanding, but so try these, and then if you want to stop, if you want, you can keep trying all of them. But if you wish, it might be wise to stop at 26. And then I'll help you guys more on Thursday with 27 and down. Even though I've already taught the idea, but I might suggest that you wait. Some of them might be real simple and you'll get it, but there might be a couple that might throw you off. So if you want to wait on 27 and down, go ahead. And if you want to wait on, I think it was 5 through 11, you can wait or try some of them, and then we can go over the rest of them on Thursday. Okay?
Okay.
So, well, that's a lot of stuff, but I hope you understand it better than before. And I think we just get tired is all. So then we starts to wear on us. So I hope this helps you, ladies. And any comments or questions besides saying that it's too long before we say goodbye?
No.
Okay, and our stamina starts to wear out, I think. Plus, I'm doing this with other classes too, so I don't know how you guys feel, but for me, I start to get tired, yeah? Mhm.
I bet. I give you props.
Yeah, so anyway. Okay, ladies, well, thank you for joining in. Thanks for your patience and stamina, and work on this. And if you have any questions, I'll have an office hour tomorrow at 10:50. Otherwise, we'll wait till Thursday and then continue and polish this section up, okay?
Okay.
Okay. Thank you, Mr.
you.
King.
You're welcome.
Have a
Goodbye.
nice one. Take care, sir.
You too. Thanks. Bye.
Bye.